in this chapter, we are going to talk about conjugation and aromaticity. And when we talk about conjugated double bonds, those alternate single bonds, double bonds, single bonds. And one of the things that we're going to talk about a lot in this chapter is benzene. Now, benzene was discovered in kind of the early 1800s by Michael Faraday, who was looking at lamp oil. But it was described by the German chemist August Kekuli, the same person of the Kekuli structures. And he pictured the ring of benzene after dreaming of a snake eating its own tail. And if you've got a good 5 minutes to go down some wiki holes, it's a really interesting kind of discussion about, like, he had been drinking and he had a dream, and this is kind of why you see this spread out throughout pop culture, right? Is this idea of a snake eating its own tail, and that looks like benzene. Now, chapter 3 introduced valence bond theory. And now when we talked about valence bond theory, which we abbreviated as VB, right? This was just a model that describes the orbitals that hold valence electrons in a molecule or molecular ion. And so remember, valence bond theory describes a single bond as a sigma bond, right? And so we said, look, we've got a single bond, and that single bond is going to be a sigma bond. And then, and that sigma bond is the result of two half-filled orbitals, the s orbitals or hybrid orbitals, overlapping along the bonding axis. And then we said, look, we have a double bond, and that's a sigma and a pi bond, okay? And then we had a triple bond, and that's a sigma and two pi bonds, okay? So that's kind of our review of valence bond theory. And remember, each pi bond is the result of two p orbitals that overlap on opposite sides of the bonding axis. Now, although valence bond theory accounts for a number of important characteristics of molecular structure, it does not adequately describe species with electrons that are delocalized by resonance. So to account for electron delocalization, we introduced the concept of conjugation among p orbitals. Okay, and then we're going to apply the idea of conjugation to account for aromaticity, which is an important property of cyclic species that impact molecular structure and stability. So we are going to start out with conjugation, but then transition to aromaticity, right? Which is something that we see in cyclic molecules. Okay. Now, towards the end of the chapter, there is a discussion of conjugation of p orbitals and how it applies to molecular orbital theory. I personally think that molecular orbital theory fits much better into physical chemistry. And so just because we can't cover all the things in organic chemistry, I save molecular orbital theory for physical chemistry. But if you are super interested in molecular orbital theory, do go ahead and read about that, but know that we are not going to cover the full chapter here. We're just going to cover up through valence bond theory. So here's the deal. What we're going to learn about conjugation and aromaticity is going to be super useful in some upcoming chapters, specifically chapter 24 and 25, which cover the reactions of aromatic species. So this is why we skip around a little bit. This is why I do chapter 14 or teach chapter 14 right before chapter 24 and 25, because chapter 14 applies most heavily to chapter 24 and 25. So there's our review, and without further ado, let's jump right into chapter 14. So valence bond theory, right, we just mentioned, that's unable to account for the resonance delocalization of electrons. And so let's look at the allyl cation. And so the allyl cation is shown here. It has two resonance structures, which is the outcome of an atom lacking an octet adjacent to multiple bonds. Now, remember, we went over in chapter 1 that this resonance structure is hypothetical, right? Each one of these is hypothetical, and the actual structure is described by a resonance hybrid, which is the weighted average of the resonance structures. So, the two electrons of the pi bond, right here and right here, are what we call delocalized over the two carbon-carbon bonding regions, right? So delocalized here and here, making both of those carbon-carbon bonds equivalent. Now, both are an intermediate between a single bond and a double bond, and the positive charge of the allyl cation is delocalized over the two terminal carbons in the resonance hybrid. So, the question may be, well, then how does valence bond theory fail to describe these aspects of resonance delocalization? And so to answer this question, we need to look at this figure here, which shows the p orbitals that are contributing to the allyl cation's valence bond picture. Okay, and so we can see the orbitals here. Each carbon is sp2 hybridized. Okay, so all the carbons here are sp2 hybridized. Okay, and contribute one valence p orbital. So for the allyl cation to have a total charge of +1, we can envision the allyl cation being constructed from two uncharged carbons and then one positively charged carbon, which is kind of shown here. That's what we envision, right? And this is why one electron occupies the p orbital contributed by the left and middle carbons, which are the uncharged carbons. So kind of like you can see here, there's the empty p orbital and these electrons here, okay? But, and when we look at this, but when we look at this, two half-filled p orbitals overlap on these opposite sides of the bonding axis, and that's what results in the pi bond, okay? This valence bond picture suggests a double bond between the left here and the center carbons. So if we look at the valence bond picture, we're going to say, look, we have a double bond here, right? And then a single bond here with valence bond theory, which does correspond to this, but not to the resonance hybrid, okay? So here's a really good generalization that we can say, is that valence bond theory accounts for features of bonding in individual resonance structures, but does not account for the delocalization of electrons in a resonance hybrid, right? And so why does this shortcoming occur, right? That would be the next question. Well, why? And so it arises because valence bond theory considers just the overlap between pairs of orbitals contributed by adjacent atoms. And so to account for electron delocalization and to overcome that shortcoming of valence bond theory, special considerations have to be given to the overlap of multiple p orbitals simultaneously. And so simultaneous overlap among p orbitals occurs when the p orbitals are all parallel to each other and are on sequential atoms, forming what's called conjugated p orbitals. And a set of conjugated p orbitals represents what we call a single pi system of orbitals, and electrons occupying a particular pi system are delocalized over all the atoms that contribute to the p orbitals of that system, which is what you see here in kind of this really ugly picture, but it's what you see here. That's what they're trying to represent here. So all three p orbitals of the allyl cation are conjugated, and that represents the single pi system. The 2 pi electrons in that system are delocalized then, so instead of showing them in the orbitals here, we're showing them here over the carbon-carbon bonding regions, and that's in agreement with the resonance hybrid that we saw on our first slide, okay? And so this is a new theory that we're applying. So let's look at that more, okay? Remember that resonance delocalization of electrons stabilizes a species, right? And so that was our big take home from chapter 1, is that resonance delocalization of electrons stabilize a species, right? And so with the understanding that resonance delocalization is made possible by p orbital conjugation, we can then make the following generalization. A molecular species tends to be more stable if its valence p orbitals are conjugated than if they were not conjugated. Okay, so because these p orbitals must be parallel to be conjugated, the stability that accompanies p orbital conjugation can have important consequences on the geometry of a molecule. So for example, the allyl cation is most stable when it's entirely planar. So this cation here is most stable when it's planar or flat. So that geometry allows all three p orbitals then to be conjugated. If one plane of the sp2 hybridized carbon were rotated, right, then what we would see shown here, right, you can see this rotation here, and what you'd see shown here is that the orbital would no longer be parallel to the other p orbitals and conjugation would be lost. So the take home here is that this is most stable when it's planar, and this is not planar here because it bends, okay? So there's a big takeaway here, okay? So there's a couple big things from looking at the allyl cation, and I've got them here written for you. So in a resonance hybrid, each atom where electrons are delocalized contributes to the p orbital of the same pi system. And then the number of electrons in a pi system is the same as the number of electrons delocalized over the resonance hybrid. And you can count the electrons by interconverting resonance structures in a way that all atoms that contribute a p orbital to the pi system are involved. So I want us to apply this to a problem. So let's look here. Which atoms in the hexa 1,3 dienyl cation contribute a p orbital to the same pi system? And how many electrons are in that pi system? So when you are asked to solve a problem like this, these are some questions that you need to think about. And so the first question that we think about is, how can you draw all the resonance structures of the species to establish a resonance hybrid? And so that obviously is going to take some space. So I'm going to come down here to do this. Okay. And remember, we're going to use these double-headed arrows between resonance structures. And I'm going to move the electrons towards the positive charge. So they're going to come right here. Okay. And that's going to make this resonance structure. Okay. And then I'm going to move these pi electrons here. And I'm just looking where my bonds go and then putting that positive charge in. Right? And so there are my 3 resonance structures. And so you can also draw so from this we can draw the resonance hybrid. We're going to come in here and we're going to draw dashes to represent the electrons delocalized anywhere the double bonds were that moved in our individual resonance hybrids. Okay, so that's where our dashes are. Then we're going to put a partial positive anywhere there was a positive charge that was on one of our resonance contributors. Okay, and so the hybrid ends up looking like this. And so in the resonance hybrid, which atoms do we see the electrons delocalized, and which atoms, therefore, contribute to the p orbital in the pi system? So the electrons are delocalized over these carbons here. So each of those carbons contributes to the p orbital in the same pi system. And the rightmost carbon here does not contribute to the p orbital of the pi system because it is not involved in the electron delocalization. So, right, we've answered the first question where we've identified which atoms contribute to the p orbital in the same pi system. So this one, this one, this one, this one, and this one. Those are the ones, okay? And then how many electrons are in that system? When we look here, right, we move electrons here, and then we move electrons here. Okay, so it says, how can you use electron movement in drawing resonance structures to indicate all of the pi electrons in the given pi system, right? So when we look at these resonance structures, they're related by moving electrons over every atom that contributes a p orbital to the pi system. So this requires moving these 2 and then these 2. So it requires moving 4 electrons. And so the pi system then contains 4 pi electrons that move. So when we answer this question, we've identified the atoms that contribute to the p orbital of the pi system, and then we know how many electrons are in that pi system. So it's just the electrons in the double bonds that we're looking at, and it's just the double bonds that move. Okay, and so that's how you would answer questions like that. Now, unlike the allyl cation, okay, butyl-1,3-diene does not have an atom lacking an octet adjacent to a double bond, and so it does not exhibit the same kind of resonance. Okay, but conjugation still explains 2 key features of butyl-1,3-diene. And so one of the features of butyl-1,3-diene is that even though this central carbon here can rotate, its rotation is hindered, and the molecule instead prefers to be entirely planar. Okay, so it sits really flat. The other thing that conjugation explains here is that the carbon-carbon double bonds here and here are longer than normal. So their length is 133.8 picometers, and that's slightly longer than the 132 picometers of ethene. The other thing that you're going to notice is the carbon-carbon single bond here is slightly shorter. It's 135.4 picometers, and it's slightly shorter than the 154 picometers that we see there. And so resonance can explain this, or not, sorry, not resonance, conjugation can explain this. And so let's look at the next kind of slide here. So let's look at the role that valence p orbitals play. So for each carbon that's sp2 hybridized, which are these carbons here, and each carbon is uncharged, and so that means each carbon contributes one valence p orbital that contains a single electron. So we've got one valence p orbital here that contains a single electron. And so for those p orbitals to remain parallel and conjugated, and that again provides stabilization of the molecule, the bonds from all four carbons must lie in the same plane. And so that's why this molecule is planar or flat. And so that explains the first thing that we see. Now, to understand the kind of strange carbon-carbon bond lengths in butadiene, remember that conjugation allows pi electrons to be delocalized, and the pi system extends over all four carbon atoms. So the 4 pi electrons are delocalized over the 3 carbon-carbon bonding regions. And so what this means is, instead of the 4 pi electrons localized in 2 terminal carbon-carbon bonds, like the Lewis structure would suggest on the previous page, all 3 carbon-carbon bonds have some pi character, which is really better seen here. Now, the additional pi bond character between the 2 central carbons results in a shorter carbon-carbon single bond than normal, and then the pi bond character between each pair of outer carbons is reduced, which results in a longer carbon-carbon bond than normal. And so when we talk about this, conjugation helps explain, or this theory of conjugation explains the experimental data that we observe.